Today's lesson will focus on proving trigonometric identities. Our objective for today is that students will be able to develop strategies to prove or disprove trigonometric identities. In our activator, we looked at the definition of the word prove and what it means to actually try to prove something to be true. You'll learn about today proof strategies, proving identities, disproving non-identities, and identities that are used in calculus. So that's what we're going to be focusing on in our instructional focus. And by doing this, it's going to provide you insights into the way mathematical proofs are constructed and how we use those proofs. So there are a handful of general strategies that we use to prove identities. So first off, the proof begins with the expression on one side of the identity. The proof ends with the expression on the other side. All right? In between consists of showing a sequence of expressions, each one that is easily seen to be equivalent to the previous. So we're kind of stepping through one step at a time from one side of the equation until we get to the other side. For example, if I was asked to prove the algebraic identity of x squared minus 1 divided by x minus 1 minus x squared minus 1 divided by x plus 1 equals 2, I would start with the left-hand side. This would be my starting point right here. Now, if I can step by step walk my way through and get to the final value 2, that essentially would be a proof for that algebraic identity. Take a couple minutes, pause your video, and see if you can reach that proof. See if you can get from the left side to the right side on your own. When you're ready, unpause the video and continue on. Welcome back. So here we can take a look at that algebraic identity that we wanted to prove. Now, the first thing that I would do in order to prove this is I would start out by factoring the top into difference of squares. So on the left-hand side, I have x plus 1 divided by, or x plus 1 times x minus 1, all divided by x minus 1, minus x plus 1 times x minus 1 all over x plus 1. The interesting thing here that we can do is we can find that this piece here and this piece here can cancel out on each of these fractions. All right, that's just 1, right? And so we can cross those out. That's just canceling out like terms. And we're left with x plus 1 minus the quantity of x minus 1. And if we distribute that negative sign, we would end up with minus x plus 1. And that's how we get to this point here. X minus x cancels itself out, and we're just left with 1 plus 1, which is 2. So if we step our way through, we're able to prove that algebraic identity. So here's a trigonometric identity that I would like for you to try to prove. Can you prove that the identity of tangent x plus cotangent x is equal to secant x times cosecant of x? Take a couple minutes, see if you can come up with a proof that would show this identity to be true. Pause your video, and when you're ready, unpause to see a solution. All right, welcome back. So if I were trying to prove this, I probably would have started with the left-hand side, tan x plus cotangent x, and I would have started out by using my identities because I see I'm trying to get to secant and cosecant, which are using sine and cosine. So I would rewrite tan x in terms of sine and cosine, sine x divided by cosine x, plus cotangent, which would then be cosine x divided by sine x. So that would be my first step. I don't know right off the bat if this is right, okay? But I have a feeling, knowing where I'm trying to get to, knowing what I am trying to prove, I need to get to that point. So I started here. Now, I see that these are combined into they're being multiplied together. That means I likely would need to find a common denominator. So that would be the next route that I take, is trying to find that common denominator. So in order to do this, I'm going to multiply the left side by cos x over cos x. I'm going to multiply the right, sorry about that. I multiply the left side by sine x over over sine x, because I'm looking for a common denominator here. The common denominator is going to be sine times cosine. So sine x over sine x. The right side by cos x over cosine x. And then when I multiply this out, I'm going to have sine squared x divided by, or plus cosine squared x. All of this is going to be divided by sine of x, cosine of x. Now, interesting here, sine squared plus cosine squared, this is one of our Pythagorean identities. This just gives us 1 divided by sine x, cosine x. I can separate this out into 1 over sine x times 1 over cosine x. Well, 1 over sine x, that's great. That's cosecant x. 1 over cosine is secant. And this is exactly what we were trying to prove. So we were able to start with what was on the left, and through simple operations, simple identities, we were able to reach what we were looking for on the right. And if we look at the actual written solution from the text, that's exactly the pattern that they followed as well. So this is really important, that even though I didn't know exactly where to begin or exactly how to get there, I was able to use what I was trying to prove to give me an idea as to where I should go. I knew that I didn't want tan and cotan. I wanted something in terms of sine and cosine, and then I knew that they needed to be multiplied together, so I knew I needed to combine them with a common denominator. Once I did that, it kind of played itself out, and we were able to reach the proof that we were looking for. All right, so you may come up against certain situations where that first set of strategies just isn't enough. We may need to look at this second set of general strategies. The first of which says, begin with the more complicated expression and work toward the least complicated expression. Okay, that's fine. We'll start complex and we try to narrow it down and trim down to something easier. It's a great strategy. Second, if we get to a point where no other move suggests itself, just convert everything into sines and cosines. It may open some doors that lead us to being able to maybe cancel something out, maybe see something that we didn't see in the previous state. The last thing we want to do is combine fractions over a common denominator. These strategies will help us when our proofs are a little bit, trickier to come by. All right, and here's an example where we may actually have to use these different strategies. So if we start out, it says match the function f of x equals 1 over secant x minus 1 plus 1 over secant x plus 1 with one of the following, and then confirm the match with a proof. Well, to match it, the simple way to do that is just to look at the graphs. My graph of my original function is here on the right, and I take a look at the graphs of the other two functions below, and we're able to see very quickly the match occurs with 2 cotangent x cosecant x. So then we want to confirm that match with an actual proof. All right, so let's go see how that proof is done. Now, if we want to do that proof, and let me slide this over a little bit, make it a little bit larger. All right, so when we want to do this proof, we are going to start with the more complicated expression. That was that first strategy, so we start here. All right, then I'm going to jump right ahead to that third strategy where it said, hey, find a common denominator. So we're going to go ahead and do that. We multiply each side by each fraction by the other denominator. So the first one, 1 over secant x minus 1, we're going to multiply times secant x plus 1 over secant x plus 1. And for the second one, we're going to do secant x minus 1 over secant x minus 1. In doing that, we're going to be left with this expression right here. When we multiply secant x minus 1 times secant x plus 1, we get secant squared x minus 1. And then when we add the top parts together, we'll notice what happens with our positive 1 and our negative 1. They cancel out, and we're left just with 2 secant x divided by tan squared x, because one of our trig identities states that secant squared x minus 1 is the same as tangent squared x. All right, so we've broken it down now to something pretty simple, but I feel like I've hit a dead end. I don't really know what to do from here because there's nothing here that really shows me how to get to cotangents and cosecants. So this is where we bring in that next strategy of, all right, you hit a dead end, convert things to sines and cosines. So 2 secant x is the same as 2 divided by cosine x. Tangent squared x is this, or 1 over tangent squared, or cotangent squared x is cosine squared over sine squared. Now when I look at this, I see, oh, I can cancel out a cosine. That immediately gave me something that I'm able to do. And I am left with 2 cosine x divided by sine squared. Now at this point I see, oh, I can take sine squared and break that up into sine x times sine x. And I can now break this down further into this right here where I have 2 times cosine over sine times 1 over sine. Cosine over sine is cotangent, 1 over sine is cosecant, and 2 is just 2, which gives us 2 cotangent cosecant, which is exactly what we were trying to prove. That second set of general strategies opened the door for us to being able to solve this problem. And it's a great set of tools that will help you as you're trying to prove identities when you get stuck. One other strategy that we haven't seen to this point is that we may want to set up a difference of squares. And you might say, well, what do you mean by that? Well, if I'm asked to prove this identity, cosine t divided by 1 minus sine t equals 1 plus sine t divided by cosine t. All right, I may need to do something. I don't really know where to go. I have cosines and sines. I haven't really learned any steps for how to move beyond this point. All right, so I'm going to start with what's on the left-hand side. To me, that's a little bit more complex than what's on the right, just because our denominator is more complicated. If we have more items in a numerator, that's a little bit easier to deal with, but when it's in the denominator, it becomes a little trickier. So I'm going to start with that, with the left-hand side. So I say cosine t divided by 1 minus sine t. And what I mean when I say set up a difference of squares is I'm looking at my denominator, 1 minus sine t, and I say, well, is there a way in which I could, or is there something I could multiply this by to somehow turn this 1 minus sine t, say, into 1 squared minus sine squared t? Because 1 minus sine squared will open some doors into changing that sine into, for example, cosine, right? Which, notice, I'm looking for a cosine on the denominator. All right, so how can I get to this difference of squares? And the way to do it is to just multiply this, remembering 1 minus sine t is kind of in parentheses. We're going to do it by 1 plus sine t divided by 1 plus sine t. Because when we multiply these bottom two binomials, we're going to get 1 squared minus sine t plus sine t minus sine squared. Well, isn't that exactly what we want? It is, because the positive and negative sine t's will cancel out, and I will be left with this difference of squares on the bottom. So when I do this, this becomes cosine t plus, and I guess I don't even need to get to this point. I don't need to actually distribute this at this point, but I'll say this is cosine t times 1 plus sine t, all divided by 1 minus sine squared t. Now, 1 minus sine squared, we know by the Pythagorean identity, is just cosine squared. So now I have cosine t times 1 plus sine t, all divided by cosine squared t. Well, my cosines can cancel, and I'm left with 1 plus sine t all over cosine t. And what do you know? That's exactly what we were looking for. The book proof goes about it the exact same way. The goal was to set up that difference of squares, because a lot of times in order to use our Pythagorean identities, we need to have our sine function or our cosine function. We need to actually, instead of it just saying sine t, it needs to be sine squared or cosine squared. So if we can set up that difference of squares, that allows us to use the Pythagorean identities, which opens some more doors. So once again, that's the thought, is if you get stuck, what tools do we have to get us unstuck, to open doors to continuing on in our proof? There's an additional set of strategies that we can use when we get stuck. So the third set of general strategies is to, 1, use the algebraic identity a plus b times a minus b equals a squared minus b squared to set up applications of the Pythagorean identities. That's what we just talked about, setting up that difference of squares. And number two, this is really important. Always be mindful of that target expression and favor manipulations that bring you closer to your goal. I've been hinting at this throughout all of the examples, but I kind of look at where I'm headed and say, well, what do I need to get myself there? If we go back, all right, and I'm going to go back to one of the earlier problems. When we were looking at example 2 and I had tan x plus cotan x equals secant x cosecant, I knew immediately, I need to have sines and cosines, and I need to get rid of that plus sign. I need to have a common denominator. I knew what I needed to do because I was mindful of where I was headed. So this isn't anything new when we give you this second set of general strategies, but it's important that you favor those manipulations that will bring you closer to your goal, meaning you have to know what your goal is, and you have to keep that in mind as you are moving. All right, so in this last example, we're going to look at how you can work from both sides. Sometimes I might not know where to go and might not be able to make it all the way with just the left-hand side. I might not be able to go with just the right-hand side. They're both complicated. But what if I work the left-hand side to something and I work the right-hand side, I get to some value, and I get the same value after working the right-hand side? Is that enough to be a proof? And the answer is yes, because if I can get to that value, then I can kind of go backwards through what I did with the right-hand side to get to our final destination. So we can work from both sides. So let's see an example. All right, we're actually going to use this example here of cosine or cotangent squared u divided by 1 plus cosecant u is equal to cotangent u times secant u minus tangent u. And we're going to try and prove this, but we're going to do it by working both sides. So let's take a look at this example where we're going to work from both sides. Let's start out with the left-hand side. All right. So if we start out with the left-hand side, we start out with cotangent squared u divided by 1 plus cosecant u. Well, I can start out by using a Pythagorean identity. We take cotangent and we convert it to cosecant squared u minus 1. And the reason why I'm going to use that is just to try and, my thought process here is I have cosecant on the bottom. Let's set up the top with cosecant. All right. That way we have at least similar, we have similar functions. All right. I also have this cosecant squared u minus 1, which I can now break down. This is a difference of two squares. This becomes cosecant u plus 1 times cosecant u minus 1. Well, notice at the bottom I have cosecant u plus 1. Well, those will cancel out, and I'm left with just cosecant u minus 1. All right, I feel pretty good about what I was able to do in simplifying the left-hand side of my equation. So now let's take our right-hand side, and let's see, can we get to cosecant u minus 1? So in order to do this, I'm going to want to get rid of these tangents. I'm going to set this up using sines and cosines. Cotangent is the same as cosine divided by sine. All right, tangent is the same as sine divided by cosine. So I'm going to go ahead then and I'm going to distribute this. And when I distribute, my cosines will cancel. I'll get 1 over sine u for the left-hand side. And on the right-hand side, not only do my cosines cancel, but so do my sines, and I'm just left with minus 1. So I get 1 over sine u minus 1, which is the same as cosecant u minus 1. But realistically, all right, we got that same thing. So our proof is essentially complete. But we would have never known to go from cosecant u minus 1 to expanding this to 1 over cosine minus sine over cosine all times cosine over sine. It's not something that I would expect anyone to know to do. But by working from both sides, we're able to get there, and then we can put our entire proof together. We can reconstruct it by saying, all right, we get to that cosecant u minus 1, which is the same as 1 over sine u minus 1, which can be converted to what we saw before, cosine over sine times 1 over cosine minus sine over cosine, which can be rewritten as cotangent times secant minus tangent. We got there. But the way in which we got there, we would have never been able to do it just going from one side. We never would have gotten here. But because we were smart enough to say, hey, let's work both sides and get to a common point, we were then able to take that last part, that second half, and just flip it, make it backwards in order to finish the entire proof. And this is a perfectly valid proof. This works. You can work both sides. And so when all else fails, if you can't figure out what to do, work both sides. See if you can find some common ground so then you can then reconstruct your proof start to finish. So in summary, in this lesson, we identified strategies that could be used to prove various trigonometric identities. We developed a plan of attack, right? You should be able to jump in and develop that plan of attack for proving a given identity. All right, if we give you an identity to prove that can be proven, you should be able to do it. Now, it's not going to be perfect. You're not going to be able to do everything right off the bat, but you should at least know how to use strategies and identities to work from one side to the other. Also, if there's a potential non-identity, can you get to something where you have something that you know is not true? All right, can you simplify it to a point where you can say, you know what, that identity, that's just not true, because you end up with something like cos x equals sine x, where we know that's not true. So can you simplify it to a point to disprove a non-identity? You should be able to do all those things, and hopefully, this was a lot to take in, but hopefully it empowers you moving forward.